Look at any modern industrial facility, and you will see a massive, highly synchronized physical operation. Millions of dollars in mechanical assets operating under immense stress to drive continuous production. But when one of those highly engineered machines breaks, the permanent digital record of what went wrong usually looks like this: two words typed hastily into a free text box. Industrial maintenance follows a rigid workflow: identify a problem, plan, schedule, and execute the repair. The final step is closing out the work order and feeding that history back to improve reliability. But this is exactly where the loop breaks. Plants spend hundreds of millions of dollars fixing physical assets, yet frequently fail to capture the specific execution history of the repairs they just paid for. Relying on free text entry creates a localized illusion of knowledge. A technician might know what fixed leak means today, but in 6 months, that note becomes analytical noise. It cannot be categorized, filtered, or trended. Work order closeout has to be treated as a structured data handoff. It is the only way a site can move past reacting to failures and actually begin learning from them. Let's look at how this data failure plays out on the floor. Take a critical asset, like pump P101. It suffers a sudden, violent mechanical failure and forces an immediate halt to production. Over the course of 2 months, this specific pump goes down 3 separate times. If we pull the work order from that first failure, the recorded action is repaired. The underlying cause is left completely blank. Physically, the pump seal flush line had become heavily plugged with contamination, which caused the seal to burn up. Because that specific cause was never captured in the digital record, the planners and reliability engineers remain entirely blind to the actual failure mechanism. Without knowing that contamination is the root issue, no preventative measures are taken. The flush line clogs again, predictably driving the second and third failures. The financial penalty here compounds rapidly. The plant pays for the replacement parts and labor 3 times over, while absorbing the cost of extended operational downtime. Poor data entry is often dismissed as an administrative annoyance, but it has a physical consequence. Missing information directly mandates extra wrench time the following week, forcing technicians to troubleshoot the exact same symptom from scratch. Without documenting the precise cause of an event, a maintenance team is mathematically guaranteed to repeat the exact same repair. Building an effective failure history requires moving past subjective descriptions. Free text notes provide useful context, but they cannot be systematically tracked across thousands of assets. The solution requires a transition to a standardized coded structure, specifically problem, cause, and remedy codes. To establish this structure, every work order closeout procedure must answer 5 very specific questions. First, what failed? We need the exact failure mode. Second, why did it fail? This defines the underlying root cause. Third, what did we do? The specific physical remedy applied to restore the asset. Fourth, what did it cost, in terms of labor hours and parts consumed? And fifth, what was the impact on production? These 5 questions define the boundaries of the minimum closeout dataset. Capturing anything less leaves blind spots in the history of the equipment. When we map this dataset onto a computerized maintenance management system, it creates a rigid template for data entry. At the top level, the interface requires the exact asset ID, the work type, and the 3 drop-down menus for problem, cause, and remedy. Below that, it captures the operational metrics: the exact failure date and time, the duration of downtime, and the precise quantities of parts used. This specific data structure acts as the non-negotiable minimum standard for closing out all corrective maintenance work. Expecting this level of data fidelity purely through workforce motivation is an ineffective strategy. People are busy, and manual data entry is tedious. The digital architecture of the system itself must be designed so that capturing the correct data is the path of least resistance. This requires building quality gates directly into the software. If a user attempts to close a work order with empty mandatory fields, the system physically blocks the action. Free text boxes must be replaced with strict drop-down menus, forcing the user to select from a pre-approved taxonomy of diagnostic codes. The system should also employ conditional logic. For example, if a user enters a downtime value greater than 0, the system automatically triggers a mandatory prompt for a downtime reason code. The same logic applies to materials. If the requested parts fall under a rotating equipment category, the system actively prompts the user for a specific component ID. But software architecture alone cannot guarantee accuracy. The human processes validating that pipeline must be equally structured. A successful closeout relies on a rigid 5-step workflow, with distinct ownership assigned to every node. First, the technician completes the physical work and inputs the required codes, technical notes, and parts data. Second, the system runs an automated check to ensure all mandatory fields are populated. Third, the supervisor acts as the human quality gate, validating the accuracy of the entered data before approving the final close. Overseeing this architecture is the CMMS administrator, who controls the code catalogs and manages the conditional rules. If these specific roles remain vague or overlap, the validation process breaks down, and data quality will inevitably degrade. Combining hard-coded conditional system logic with strict assigned human validation is the only reliable way to safeguard an organization's failure history. Once the architecture is in place, data quality must be tracked with the same operational rigor as site safety metrics. This dashboard displays the primary indicators managers should monitor weekly: completion of required diagnostic codes remaining above 90%, and verifying that all applicable downtime is accurately captured. But the ultimate indicator of system health is the usage rate of the miscellaneous code. If miscellaneous becomes the most utilized failure code, it proves the existing taxonomy is missing critical categories, or the workforce requires retraining. To correct errors quickly, an automated exception report isolates invalid entries and routes them directly back to the accountable supervisor for correction. When deploying this framework, limit the initial scope. Start with a 60-day pilot program, focus strictly on a single, highly critical asset class, and do not overload the software with hundreds of codes on day one. Baseline the system using only the top 20 critical failure codes to prevent user fatigue and ensure high adoption rates. Work order closeout is the final bridge between executing a repair and preventing its recurrence. Architecting a rigid, systemic data pipeline at this exact stage is the essential requirement for moving a site from reactive maintenance to continuous reliability.